right, good morning, everyone. A lot of chit-chatting going on out there. So just remember that the computer exam is ongoing, right? So make sure that you're not, if you've taken it, make sure you're not discussing this with people that have not taken it or even discussed it around them, right? It's just not fair. It's just not fair. Okay, so the computer exam goes until tonight, 8:30 tonight, and after that, just like before, the second copy of the computer exam will open up, and you have until Friday at 11:59 p.m. to revise that and to submit a second exam if you would like to. Okay? Do I have something else to say about that? The final exam, I know we're not done with this one, but yeah, something to look forward to. We always have to have something to look forward to. And that's essentially the end, right? Is on Friday, so the in-class exam is on Friday the 26th from 9:30 to 11:20. The computer exam will go from right after class at 11:30 until Tuesday at 10:30. Okay? Yeah, question.
Is there any way you could open up the computer portion for a day earlier? On Thursday rather than Friday? Or is that just not able to happen?
Well, so the question is, can I open it up earlier? Usually I'd like to have everybody do the same thing. So everybody take the written part first and then take the computer part. Instead of having, so everybody has the same sequence of steps. If somebody ends up in a real bind, then talk to me about some special arrangements. Okay? Of course, for the final, you don't get to redo the computer portion of the exam. Okay? If I were you, I would go ahead and reserve a time slot if you haven't done that already. Okay? Because I have had the experience of when the whole testing center fills up and people can't get a slot. So do that as soon as possible. Okay? Question?
Is in class in this room?
In class will be just like on the other exams, will be split between two rooms, and I'll announce all of that as we get close. Yeah, question?
So was the 9:30 to 11:20, do we get that full 1 hour and 50 minutes? Or is that just the time slot for the final?
9:30 to 11:20, we have that whole time in the lecture halls that we have. You can use the entire time if you want. I won't, I'd like to kick you out earlier because it's kind of boring to watch you take those exams, but I'll let you have the whole time. Yeah?
Is the final exam portion going to be significantly longer than our past exams?
Okay, good question. We have some more time. It will be longer, but not double the amount of time. So usually we've had 4 questions on the written portion, and so typically on the final I have 6. Instead of 4. The multiple choice will not be doubled as well. It'll go from, we've been having 25, probably just up to 30 questions. Okay? So there is more, but not twice as much. Good question. Anything else? Yeah?
How much new material versus old material will be on the test?
Okay, so we're finishing up this section. We have some more chapters to do before the final. The final will be comprehensive. The new material is essentially a quarter of the class material if we split it up into 4. So I would expect 25 to a quarter to a third or something like that over new material. But of course, you can't do the new material without knowing the old material, so even if I ask you something new, it's comprehensive as well. But it won't be like half specifically over the last material or something. It'll be spread over the whole year, in fact. Yeah?
Is it just 1 hour on the computer portion again, or will it be
No, on the computer portion, it'll probably be an hour and a half. I think that's what I set it up for, something like that, if anybody's looked at that thing. Yeah, okay. Anything else? Yeah, question?
So you mentioned that it's comprehensive over the whole year. Are you just saying that includes, like, we'll have to know the simple things from last semester, or will you ask a specific question?
No, I won't ask specific questions like, draw me the mechanism of an electrophilic addition reaction of an alkene, right? However, you might need to know reactions from last semester to do synthesis, just like we've been doing, okay? And of course, we can't understand anything from this semester unless we understand last semester. But yeah, I won't specifically target, mechanisms or predict the reaction product or things like that over reactions from last semester. Anything else? Okay then. I don't have a clicker today because you guys are too busy answering questions already. What I will do though is I will post just your total clicker points, or what I'll probably post is if you have more than 20, I'll just remember the clickers are for extra credit points and you can apply a maximum of 20 points to your grade. Okay? So what I will post is if you have more than 20, I'll post that you have 20. If you have less than 20, I'll post what you have up to now. What I noticed, so I hadn't really even looked at those things until I think yesterday. And of course, this is the way it always is that, so there are a lot of scores that people have been adding up, but their clickers aren't registered to them yet. So what it shows me is that it gives a clicker number and all these points, but it doesn't know who the clicker belongs to. All right, so if I upload these points into a column and you've been taking the clicker questions the whole time and there's no points showing up, then it means that you haven't correctly registered with the iClicker thing, okay? So if it is that situation, then what you need to do is go back and look at iClicker questions in the syllabus. And that gives a description on how you need to register your clicker or your phone, whatever you're using, okay? So go to the syllabus and follow those directions, all right? I'm not gonna remind everybody over and over to do this, okay? It's up to you to have that registered, and these are extra credit points, and so if you don't do that, you won't get the points applied to your grade, okay? Any questions? Okay then, let's think about where we're going now and where we've just come from. So we have just come from, something like 3 or so chapters on, or maybe even 4, on carbonyl compounds, right? We started out with carboxylic acids, and we talked about, aldehydes and ketones and all the carbonyl derivatives with strong nucleophiles like hydrides and Grignards and organolithiums and all of that. Then we talked about aldehydes and ketones with weaker nucleophiles like cyanide and amines to form imines or enamines, and alcohols to form acetals and hemiacetals, and so we did all of that chemistry. Then we went on in the last chapter to talk about carboxylic acids and their derivatives again, and in many of these we were looking again at weaker nucleophiles then. But what we particularly targeted is these nucleophilic acyl substitution reactions, right? We're converting mostly one type of carboxylic acid derivative to another type of carboxylic acid derivative. And so now, So up to now, except for acid-base chemistry of carboxylic acids, we have only been really looking at reactions where a nucleophile reacts with the carbonyl carbon of one of these carbonyl functional groups, okay? So now we are going to look at a completely different type of reactivity associated with carbonyl groups, all right? And this focuses on what is called the alpha position, okay? So the alpha position, we could draw all of these carbonyl groups like this. The alpha position is the position adjacent to the carbonyl, okay? So for all of the different carbonyl functional groups, except for ketones, they will have one alpha position, okay? For ketones, we have carbons on either side, so they have two alpha positions, all right? And so there is going to be a different type of reactivity that we will see, and essentially what we're going to see is that this alpha position is now going to be acting as a nucleophile. Okay? So we've always looked at carbonyl groups as electrophiles, but now we're going to see that they can actually be nucleophiles as well. All right? In this chapter, what we will do is whatever nucleophiles we can form here, we will look at those nucleophiles reacting with simple electrophiles like halogens and alkyl halides. Okay, so they'll essentially do substitution reactions. In the next chapter, chapter 24, what we will look at is the nucleophiles we can generate at the alpha position reacting with carbonyl groups as the electrophiles, right? And so this is going to be, all we're doing in each of these cases, so all we're really doing here is adding a new nucleophile. And then we'll look at the same kind of reactions we've seen before with other nucleophiles. Then we're going to go on to the next one. We're going to look at this new nucleophile we just learned with the electrophiles that we just learned of here. Okay, so some of those might be dimerization between two ketones or two aldehydes or two esters or cross coupling between those two, and so we'll see a bunch of different combinations of those. Okay, but all we're really doing is at first adding a new nucleophile, and then we're just looking at that nucleophile with the range of electrophiles that we already know. Okay? Okay, so the first thing that we're going to do is we're going to focus in on the reactivity of this position alpha to the carbonyl group. Okay, and as we see these reactive, or that alpha position is going to be reactive either as an enol, and we've seen enols before, or what we call an enolate, which is an anion at that position. Okay, so we're going to first look at the reactivity there and then look at the process of forming enols and the process of forming enolates, which is conjugate base. So, up till now, this is just a summary. These are kind of the reactions we've already seen. Nucleophilic acyl substitution. This typically happens, right, when Z, whatever that is a leaving group. Okay? And in this reaction, then what we did is this substitution reaction. We got our nucleophile attached to the carbonyl, and the Z group functioned as a leaving group. Okay, so this is what the carbonyl or the carboxylic acid derivatives could do. If Z is not a leaving group, so if it's a hydrogen or an alkyl group, right, aldehydes and ketones, then we did nucleophilic acyl addition reactions. Okay, so we added this, and then we'll just say, then we're going to add, Then we add water after that, or dilute acid, then H2O, and what we get is an addition, right? So on the oxygen, we add an H. On the carbonyl, we add, the nucleophile. Okay, so we add the nucleophile on the carbonyl position and the H on the oxygen. Okay, so it's just an addition reaction, just like adding HBr to an alkene, right? H on one position, our nucleophile at the other position. Okay, so we're going to look at one type of reaction here, which is basically, I think they classify it as an electrophilic substitution. So we're doing a substitution, and the carbonyl, the alpha position, is going to react with an electrophile. But we're going to turn the carbonyl compound into a nucleophile. Okay, we're going to do that either under basic conditions. So the enolate substitution is going to be under basic conditions. All right, and in general, we're going to look at this in more detail. What's going to happen is the alpha position is going to be deprotonated. So this is just an acid-base reaction here. We'll look at why that's acidic enough to do this in a minute. We form then an anion like this. And that anion can act as a nucleophile. So it reacts with whatever our electrophile is. And the result is we've replaced a hydrogen with the electrophile. Okay? So we still have one H there, right? All right, so that's under basic conditions. We can also do some of these reactions under more acidic conditions. Okay, so are we going to form this is called an enolate anion. Are we going to form the enolate anion under acidic conditions? No, because it's very basic. You can't form basic species in an acidic solution. Okay, so what we're going to form first, and we'll look at the mechanism of this. Oops. Is this species. Remember, this is called an enol. So ene because we have an alkene, and ol because we have an alcohol. All right? Where did we form enols before? Where did you see them before? Yeah.
So there was a section last semester with keto enol thought of.
Right, and what was that connected to? What chemistry? Where did we... There was a reaction where the enol was a... Right, so it was with alkynes. So when we did a hydration reaction of an alkyne, we added an H and an OH to the alkyne, to one of the pi bonds of the alkyne. That formed an enol, right? And that enol could tautomerize to its keto form. That would be going back that direction. Okay, so out of these two species here, that's the enol, this is the keto form. All right, but what we're going to see now is a reaction of an enol. So what we can think about that enol is really, this is just an alkene, right? And it is an alkene that has more electron density at the position away from the OH, because these electrons can donate electron density down to that position. Okay, so what can happen now is that this can react, with our electrophile. And what it tends to do is react like this. These come down to reform the pi bond, and the alkene portion of the enol reacts with the electrophile. And so then what we get is another intermediate that now has the electrophile at the alpha position, right? But because we're in acidic medium, this intermediate has protonated up on the carbonyl. And so we get to our final product just by deprotonating. Let's just draw a minus H plus here for now. And so we've essentially accomplished the same thing. We've done a substitution, replaced the hydrogen that was in the ketone at the beginning with whatever this electrophile is. Okay? Yeah, question?
Since this is in acidic conditions, isn't there a competing reaction where ketone gets protonated into an alcohol?
Okay, so, well, a ketone can get protonated, but it doesn't get protonated to an alcohol, right? And in fact, this is the last step here. If we started, for an example, if we started with this ketone, we could protonate on the oxygen, but all we have is a protonated ketone then. It's not really an alcohol, right? And when we saw this before, what we usually did was we said that this activated the carbonyl carbon to a nucleophile. Okay, but in this case, we're not going to give it a nucleophile to attack at that position. We're going to add an electrophile, so that's going to react at the alpha position. Okay? Any other questions? All right, so what we're going to do now is we're first going to look at this process, this initial process to form the enols. Okay? And then we're going to look at that initial process over there to form enols. And then we'll get to the reactions after that. Okay, so we can, in fact, we showed it with acidic conditions, we can form enols under basic conditions as well. So it's essentially catalyzed under acidic or basic conditions. Okay, so let's look at both of those mechanisms first. Okay, so in this case, what's going to happen is that this hydroxide, or our base, is going to remove an alpha proton. And we're just going to draw these electrons right in there to form an enolate. This has H left. It has a minus charge at that position. Okay, so let's pause right here and let's ask ourselves, why can it even do that, right? So usually we've seen that hydrogens or protons that are attached to carbon are not very acidic, right? In fact, most of them are extremely non-acidic. Okay, what's really the only type of proton bound to carbon that we've been able to do acid-base chemistry on before, up to this point. Right, making an acetylide anion. So if we have an alkyne, a terminal alkyne, we've been able to, with a strong base, pull off the proton on the end of an alkyne to form an acetylide anion. That's the only place that we've really done acid-base chemistry on protons that are bound to carbon. Okay, but here I'm showing us doing just that. And it's not forming an acetylide, it's forming this enolate. So why can we do it in this case and not in most other cases?
Is it because that carbon right there is the electrophile? So the one in the carbonyl, you draw any more electrons from it?
Well, so I think what you're suggesting is that maybe that anion is stabilized because the carbonyl is pulling electron density away from it? Is that what you're saying?
No, I'm saying, maybe I didn't hear the question correctly. So the reason why we could deprotonate that hydrogen in the first place from that carbon is because I thought the carbonyl carbon is electrophilic, and so it's drawing in electrons, so making that other alpha carbon a little bit less, you want to hold on to his electrons more, and compared to the other.
Okay, I guess what I'm hearing from you is that there's essentially an inductive effect from the carbonyl-carbon because it's delta plus, pulling some electron density away. So remember, if we're just looking at acid-base chemistry, what we're saying, if we can deprotonate there, we're saying that that proton is acidic enough, meaning that its conjugate base is stable enough that we can do this process, right? So an inductive effect is one thing that might stabilize that conjugate base, right? Making it stable enough that we can do this acid-base chemistry. So is there anything else? Yeah.
I mean, along those same lines, isn't there some sort of resonance? I mean, those lone pairs can donate and then double bond can go to the oxygen.
Exactly, and so this is actually the bigger effect, right? So what we want to be able to do to stabilize the anion, we want to be able to pull the electron density away and to share it over multiple atoms. Okay, there is some inductive effect, but resonance is usually a stronger influence. All right, so we basically have an atom with non-bonding electrons adjacent to a pi bond. This is a perfect scenario for resonance. Okay, so we have another resonance structure that now has the minus charge up on the oxygen. All right, so we have a situation where the minus charge is spread between the carbon and the oxygen. So we have a partial minus on the carbon, partial minus on the oxygen. Which of those two structures do you think is more stable? Right, the one on the right is actually more stable because why? Because we have that minus charge on the more electronegative atom, right? Oxygen can better hold a minus charge than carbon can. Okay? So this would actually be a little bit more stable. Oops, stable. So it means that in this resonance, there's a little bit more delta minus on the oxygen than there is on the carbon. Okay? Alternatively, what that means is it's more stable with minus on the oxygen, it's less stable with the minus on the carbon, so the carbon is actually the more basic end, because it's the less stable minus charge part of it. Okay? And we'll see that in a minute. So now let's see here. We're going to the enol. So what's going to happen is we can draw it from this position here. We have water. We'll show this minus deprotonating water. And if we do that, then we have an OH like this. We formed our enol. Okay, so essentially what we do, we deprotonate first because we're in basic conditions, and then we reprotonate, but on the other end of this enolate anion. Okay? So that's one way that this process can be kind of catalyzed. All right, so we can also do it under acidic conditions. So what's going to be the first step if we do this reaction under acidic conditions? It's going to be to protonate it, right? We can't form an enolate in acidic conditions, but we can protonate this oxygen. All right, so by protonating it, like we saw before, it does make the carbonyl carbon more electrophilic, but it also increases the acidity at the alpha position. Okay, so now we can use our water molecule here as a base. And it can go like this, pull off one of these, and I'm going to show the carbon hydrogen electrons go up to here. And then we are going to push these electrons up like this. And if we do that, we have our OH, we form the double bond like this, and we formed our enol. Okay? So notice, we're kind of doing the same steps, but in acid versus base, we're doing them in opposite order. Right? In basic conditions, we deprotonate and then we reprotonate. Under acidic conditions, we protonate first and then we deprotonate. Okay, so those two steps kind of are reversed. Yeah?
So why is the alpha carbon more acidic?
Okay, the alpha carbon is more, you mean in this case?
Yeah, acid.
So in acid, it's more acidic because when we deprotonate this, we get a stable conjugate base, right? This is less stable because it's protonated. We can deprotonate it and get a neutral conjugate base of this acid. Yeah?
So in both cases, we're establishing some equilibrium between our keto and our enol form.
Mm-hmm.
Is there one of these two conditions, basic or acidic, that's going to favor, say, enol more than the other condition?
Okay, good question. So the question was, we have these two reaction mechanisms, right? We have the same product, our product and reactant in both cases. And can the different conditions influence the relative ratios of product to reactant? Okay, so what do we think? Okay, so when we talk about the ratio of product to reactant, what are we talking about there? What kind of energy?
Equilibrium.
Right, it's an equilibrium, right? So what influences the position of the equilibrium? Right, the relative energies. Just the relative energies of the product and the reactant. So this is thermodynamics, right? Each for this reactant and this product, it has a certain equilibrium constant, and that's just determined by the relative energies. Okay, based upon that, answer your question. Do you think one of these can give a different ratio than the other one? No, it can't, right? Because in both cases we have the same product, same reactant, same energies. Okay, so what we're essentially doing is we're catalyzing these reactions. And so when we catalyze reactions, if we think about a reaction coordinate diagram, what are we doing to the energies when we add a catalyst? We're just reducing the height of the activation barrier. Okay, the energies of the reactants and products stay the same, so the equilibrium constant is the same, but we reduce the activation barrier so the reaction takes place faster. Okay? Okay, so to influence the position of the equilibrium, well, it's hard to influence it, but different ketones or aldehydes will have different ratios. Okay? And under basic conditions, well, not with the enol so much. So let's look at some different ketones here. Okay? So let's draw an enol of cyclohexanone. Okay, so go ahead and draw the enol of cyclohexanone. Okay. So remember when we draw the enol, what's going to happen is one of the H's on the alpha position is going to go up to the oxygen, and the double bond is going to shift from the carbonyl to a carbon-carbon double bond between the carbonyl carbon and the alpha position. So like this. Okay, we can draw it to the other side as well. In this case, because cyclohexanone is symmetrical, they would both be the same. Okay? So, if we have this keto-enol equilibrium, it turns out that the ratio in solution is about 99% of the keto form and only 1% of the enol. Okay? If we have two ketones like this, we could call this a beta diketone. Okay, because if we start with the one on the left, if this is the alpha position, this would be beta. Okay, so the two ketones are apart like this. So draw what you think is the most stable enol of this beta diketone. Okay, so in fact, each of those ketones, how many alpha positions does each of those ketones have? 2 alpha positions, right? It has an alpha position there, and it has an alpha position over here. So let's call these alpha in the middle and alpha prime over here. So which of the alpha protons is going to more easily be transferred up to the oxygen to form an enol? Alpha or alpha prime? Alpha in the middle, right? So the most stable enols of a beta diketone or beta dicarbonyl will be one where the double bond of the enol is conjugated with the other ketone. Okay? So these two are now conjugated with one another. Right? That's more stable than if we show the enol the other way, and we essentially have an isolated enol. Okay? The other reason why this is more stable is because the way I've drawn it here is that right here we can get an intramolecular hydrogen bond. Okay, so that oxygen just kind of reach around and be attracted by the carbonyl oxygen. It's like a 6-membered ring. It's a very stable size.
So because of that stability, is that why the second carbonyl group won't also?
Yeah, so good question. So I can see what you're getting at. So there are several other enols we could draw here. Okay? One, which would be of equal energy, would be this one here. Right? So those are equal. But we could also, here, let me draw the other two. We could have we already talked about this. We could have this enol. Right? That could have an intramolecular hydrogen bond as well, but the alkene is not, the two double bonds are not conjugated. Okay, so that's less stable. So the question, though, was about what if we formed enols of both ketones. Okay, and so that's possible, but I think that that's going to be even less stable. There is going to be, we could still have some intramolecular hydrogen bond, but not to both sides. Okay, so these two are going to be the most stable together, and we can see this by the fact that the ratio here is that these two, which are equivalent here, make up 74% at equilibrium, where the diketone like this is only 26%. Yeah.
So with these two structures that you have underlined,
Mm-hmm.
you told us to conceptualize the OH bond as we have one OH sigma bond, and then we have a hydrogen bond between that hydrogen and the other oxygen.
Yeah.
Is it okay, like, can you conceptualize that just as two partial sigma bonds? Like, does the resonance allow for that, or is that just...
Oh, okay. So you mean, so kind of like, could this oxygen be kind of
Yeah,
equally between those two?
yeah.
I think because if we start to make a full bond over here, this oxygen now has to have a plus charge on it, right? And we'd have to start generating a minus charge on this side, right? So I think that if we were going to draw that as resonance, this one like this is much more stable than having this oxygen actually connected to the other side. Right, so I think the hydrogen bond side is help stabilizing that, but it's much weaker than the actual sigma bond as drawn. Okay, yeah, question?
Are all ketones in aqueous solutions constantly tautomerizing to some extent?
Yeah, so the question was, is this, in aqueous solution, is this always happening? Yeah, absolutely. Okay, it's just that some of them, like a normal ketone up here, has only a very small amount of enol. But we have these specific examples where that enol can be a much higher proportion. Yeah?
And just to follow up to her question, she said aqueous solution.
Mm-hmm.
So if we have some solvent, does this keto enol tautomerization, does this only occur in some sort of solvent where we can have a proton shuttle, or would this happen in the pure compounds?
So the question was solvent effects, right? So I think that it's going to most easily happen if we have a solvent system where protons can be transferred easily. So water, aqueous solutions, alcohol solutions would help it happen. But it also, like we showed on the previous slide, it happens much more easily if that solution is acidic or basic rather than just being neutral. Okay? All right, so let's look at this last one. Draw out the enol of this last structure. Okay, so what does that look like? Is it anything we've ever seen before? All right, so this we just call phenol, right? So where do you think the equilibrium lies in this bottom reaction? Way on the phenol side, right? So this is essentially 100% of phenol because we now have an aromatic ring, and this is like way more stable than that was here. Okay. Enol formation. Let's think about forming an enolate with various carbonyl groups. Okay. So if we've got a ketone, we have an amide, we have an aldehyde, and we have an ester. All right, so let's just start out by drawing the enolate anion for each of these. Okay, so I'm just going to draw the minus charge on the carbon. I think this is good enough for this. Okay, so here's the enolate for the ketone, right? And each of these would have, if we draw it, would have a plus and H plus here too, right? Okay, if we draw the same thing for the amide, the minus charge, and we have two CH3s. Okay, so there's another one. Here's the aldehyde. And the ester. Okay, so what we want to know here is as we change the functional group, right, to a different type of carbonyl, is it going to affect the acidity? Is it going to affect the pKa of the alpha positions in each of these different types of carbonyl groups? Right? You think they're all going to be the same? No, there's no reason for that, right? So basically, whichever of these conjugate bases is more stable, right, it means that the alpha position at the conjugate acid part is going to be more acidic, right? So we're trying to stabilize an enolate anion. Okay, so we have to think about what these other groups that are attached to it typically do. All right, so let's think about the amide. Okay, what have we usually talked about that nitrogen in the amide as doing that might influence the stability of the enolate anion? Right, it's usually it donates, right? So the nitrogen is good at donating electron density, right? And that's why we said the amides were the least reactive at the carbonyl carbon, right? Because there's less delta plus there, right? It influences the carbonyl stretch in the IR. You know, it has a bunch of different effects. So if it's donating electron density, is that going to stabilize or destabilize the enolate? It's going to what? Destabilize it, right? If we have an anion and we try to donate electron density to it, that makes it less stable. Okay? So this is going to actually be the least stable. Okay, which of the other functional groups would be the next least stable on the conjugate base? What's the next best electron donating group? Yeah, the kind of the ethoxy group here, right? So the ester, right? The oxygen there can also donate electrons, not quite as good as in the amide. So this is the next least stable. Okay, what about, so we got, what we have left is the ketone and the aldehyde. Which one is going to be the next least stable? What's better at donating electrons, a methyl group or a hydrogen? The methyl group, right? So let's think about it in the other sense. So let's talk about in order of stability of the conjugate base. Okay, so the most stable conjugate base is going to be the aldehyde enolate. Okay, next is going to be the ketone enolate. Right, the ketone enolate is a little bit less stable than the aldehyde enolate because that other methyl group is donating electron density, destabilizing. The next stable is going to be the ester enolate and then the amide enolate. And so what about acidity? What order? Sorry, I know we're out of time. What's going to be the most acidic? The same order, right? The aldehyde enolate, it's got the most stable conjugate base, is the most acidic. Then the ketone enolate, then the ester enolate, then the amide enolate. All right? So we will continue on this tomorrow.